Okay, describe surface tension, capillary action, and viscosity. So surface tension, the definition is the energy required to increase the surface area of a liquid by a unit amount. Often those definitions, though they're correct, don't give us as much information as we'd like. If we just look at the top of a surface, or the surface of water, we have all these water molecules. They're jumbling around, but they generally are attracted to each other through intermolecular forces that are holding them together like a chain, and or like a set of people holding hands together, like playing Red Rover when you're a kid, if you did that. And but if you put some object on the water, say it's looks like a ball, but say it's the we're looking lengthwise down a pin or a needle, the water molecules, instead of just getting out of the way, as you might expect, they hold together and they resist that force of the pin or something small or something that is spread out across the water's surface. Instead of just getting out of the way, they hold together and they react against it. And it's due to the intermolecular forces that are holding the water together. And that's really it for surface tension. We haven't talked about the intermolecular forces, so just to point out that, we have these water bugs. You see those that skitter across the surface of a creek or a pond. They have, if you look at their feet, they're very feathery looking kind of things. It gives them a lot of surface area. It gives them a lot of buoyancy. So that's because of the intermolecular forces. Now, detergents, surfactants, just soaps, they break those bonds. So if, not that you want to do this, but if there's a water bug and you just put in a small amount of oil or detergent, they'd fall right through because these bonds are broken. Don't do that, that's me. But that's how you would drown a water bug. Okay, so capillary action, or capillary rise, is where you have a container of water and you have a very thin tube. It has to be very thin. And you'll notice this with a straw or any kind of tube you put into water. The water rises up into the tube. Now we're going to kind of expand this area out. Across this, the surface of this water that's gone above the surface of the container, you have water molecules, and they're attracted to the sides of the container. Water is very polar, and it likes the glass or the plastic or whatever it's attracted to, and it wants to ride up the wall of the and attract itself to the dry parts of the wall. But in the process, it drags behind it, just like this is a chain here. They have a chain here, and it drags the water behind it. Now, so it can't just have one water molecule that creeps up the sides of the container. They're attracted to the sides of the container. Each water molecule is then pulled on by the others, and it just drags the rest of the water layer up. And if you look closely at the sides of a container, or like you'll see that the water on the sides, in a very thin capillary tube, you'd see that the water is higher on either side. And that's, again, due to intermolecular forces. So the water wants to ride up the side, but it can't just do that. It has to drag the bulk of water behind it. Eventually, it gets so heavy that gravity pulls it back down and you reach equilibrium. Now, viscosity is the resistance to flow that is exhibited by all liquids and gases. And that's due to, water molecules, or any molecules, if they're liquids, as they're moving along, they're attracted to one another. So they want to flow, but they also have to get past each other. They kind of jumble over each other. So as one water molecule's trying to make its way through, it has to get through this maze of other water molecules, some moving slower, some stuck to the sides, and they all pull on each other and make this great mass of water that slows it down. Now, water flows pretty freely, but if you're trying to get it through a pinhole, or you have just a very thin layer of stream of water moving along, they pull each other back, and they attract each other so much that if you say you have this thin layer of water and it's right on the edge, you notice that it actually just kind of hangs there, and because it's being attracted to the surface, and all the water molecules are attracting themselves and pulling away from that movement forward. So the more intermolecular forces there are, and the heavier the molecule is, the more viscous it tends to be. Oil can be very viscous, and those tend to be molecules that are very long and very branched. And so when you have, so you picture, if you try to pour out a container, let's say a pan filled with BBs, that pours out pretty quickly. They're small, they don't really affect each other very much. But try to pour out a pan of cooked spaghetti. You can do it, it'll all come out in one clump, but if you try to just pour it out slowly, you can see all the spaghetti is really wrapped up with all the other spaghetti noodles, and that slows them down. So there's the size of them, the weight of them, and the intermolecular forces that slow down the movement of molecules, and that's viscosity. Now, determine the different intermolecular forces. Describe them. There are three that we have to concern ourselves with. We have, let's go in the order here. We have dipole-dipole forces. These happen between polar molecules. Let me I'm back to where I need to be. Molecules. Then you have London forces. Well, let me just finish that thought before we go on. So if you have something like HCl, this is slightly positive, slightly negative. And if you have another HCl that comes up in the other direction, it's flipped around, then they attract each other. And you have a chlorine here, it's going to be attracted to this hydrogen. There's a chlorine here. These are all jumbling around, but they're all there's going to be a slight attraction between the slightly positive and slightly negative sides of all the molecules, and that's going to draw them together. So any polar molecules, and they don't have to be the same. You can have HCl and water, and that's why they mix so well, is because of the dipole-dipole forces. Now, then we have the London forces. And sometimes this is called the instantaneous dipole force, or forces. And it's easiest to do with an atom. Let's say we have beryllium here, and it has 4 electrons. And they tend to be evenly distributed around the nucleus, but if we have, so the beryllium here represents the nucleus, if just for a short period of time all 4 are found on the same side, then this side will be slightly negative, this side will be slightly positive. It's an atom, that's all that there is, but it's not a whole extensive molecule, but it can still be slightly negative and slightly positive. So another beryllium that comes up will be affected by that, and it'll go in the opposite direction, try to match up the charges, and they'll be attracted to each other. So even like things like helium, which are very small atoms, just 2 electrons will attract each other and will liquefy. So since everything liquefies and everything turns to a solid, when you cool them down enough, that means that there's some forces holding them together. So we have London forces. They are found in all species. So if I give you a set of molecules and I ask what forces are there, put London forces first. London. So if I give you 5 different molecules, just write London, 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 London. Because they're all present in every single species, no matter what it is. We're going to just deal with molecules, but they're present in ions, they're present in atoms, they're present in everything. Then the last one is hydrogen bonding, and this has to be, what will result in hydrogen bonding is if there's hydrogen connected to an oxygen, hydrogen connected to nitrogen, or hydrogen connected to fluorine. So, and then this can go on to bond with something else, so can this. But HF, that's just hydrogen fluoride. We can't have anything further than that as far as the bonding. So it's either HF or it's a molecule that contains HO or HN. And let me just make sure that yeah, they don't distinguish. That's generally the three that we are concerned with. Very electronegative atoms. So if you have water that has nothing but HO bonds, so that definitely has hydrogen bonding. And what happens is this slightly positive, slightly negative, slightly positive, and the oxygens each have lone pairs. So this hydrogen, which is slightly positive, has lost a lot of its electron density. So it has kind of an empty orbital, and it is attracted to the lone pair on another oxygen. So it's really an overlap of orbitals. It's a coordinate covalent bond to some degree. It's very strong. So if you have a molecule that contains hydrogen attached to an oxygen, not just hydrogen and oxygen, but hydrogen attached to an oxygen or to a nitrogen or to a fluorine, you have hydrogen bonding. So, alright, so I didn't write them down here, but indicate which intermolecular forces are found in a sample of each of the following compounds. So let me just write some out. HCl, BF3, I'm going to write this one out completely. Oops, we want to do this. And then this one. So this is dimethyl ether. Don't need to know that to be able to answer this question. And let's do, let's say, argon. Okay, so looking at HCl, we know that we should know from our work with the molecular geometries and bond angles that this is a polar molecule. So this has dipole-dipole forces. D-D is how I usually describe dipole-dipole bonding, and I accept that on the exam. And then this has London forces. They all have London forces, but now for this guy, it has, how about hydrogen bonding? No, the hydrogen is not connected to an oxygen, nitrogen, or fluorine, so no hydrogen bonding. BF3, let me put it up here. BF3, it's a nonpolar molecule, so no dipole-dipole forces. No hydrogens, so no hydrogen bonding, but it does have London forces. How about this guy? Now it has, it's harder to see this, but there's no polarity here because there's actually there's there's a slight polarity, but I would say in this case we don't have any dipole-dipole forces, but we do have London forces. How about hydrogen bonding? The big point here for this one is that the hydrogen is not connected to the oxygen, so this one is no hydrogen bonding. For this one, since it'd be hard for you to determine if there's a dipole, I would ask, is there hydrogen bonding? Or of these, which one have hydrogen bonding? No hydrogen bonding here because the hydrogen is not attached to the oxygen, but this one is. So this one would have H bonding. It has London forces. It actually has a dipole-dipole force too, but I won't give you anything tricky where you can't quite guess whether or not it's polar, but you should be able to tell if it's hydrogen bonding. And then, so I'd stick with these ones that you've done before, that you've been able to determine whether they're polar or not. And then argon doesn't have any hydrogens, no hydrogen bonding. It doesn't have any dipole because there's only one atom, but it definitely has London forces. Has that instantaneous dipole.